Okay, so I hope the organizational problem will be solved. So concerning this set of lectures, just a few introductory words. This is meant as 6 lectures introducing you to one of the most frequently used and, I believe, important techniques which physicists employ to understand many important, or as it's conventional to say, universal features behind Anderson localization in one particle disordered systems. The name of this technique is supermatrix nonlinear sigma model. I think this is probably correct notation. In fact, first 4 or even maybe 4.5 of my lectures won't have any reference to Anderson localization at all, and will be used to introduce notions and vocabulary which will be later on used to discuss some localization related properties, which I hope to achieve in the last 1.5 or maybe 2 lectures. From this point of view, in some sense, these 4 lectures will be detached from the main thrust of this workshop, Anderson localization, and rather they could be considered as a kind of introduction into supermatrix methods of investigating random matrices, as we shall see. But don't worry, in the end, I hope, depending on actual pace, we will discuss something meaningful related to Anderson localization. Okay, I will be using transparencies for which I hope, at least this was my goal, they are self-contained and are quite detailed, in fact. We will go slow through them, and I think, it depends of course on your preference, but I think the arrangement starting from next lecture will be as follows. I will try to copy transparencies for the following lecture. Today I had no, unfortunately, I didn't manage to do it beforehand. So you will have copies of all these transparencies, and probably, at least for many of you, it will be just useful just to make notes of additional information which I will provide unavoidably, although they are quite detailed, but of course something is always left behind. I think this is the most efficient method, but of course you may try just to make your own notes. It's as you please. Just that I think that it will be not that easy given the amount of material we are going to cover. So this is, and I apologize that today I was not able to provide you already with this set of notes, but next time I will give you hopefully just copies of 2 first lectures before the second lecture. Okay, so it was very fortunate that Leonid covered finite dimensional Hilbert spaces, because it's precisely what we start with, and immediately we encounter this difference in definition of scalar product that Martin mentioned. These are 2 communities, but I think this won't be misleading, and along the way you will notice probably many other differences, but I still hope that this is self-contained and all definitions will be given, and therefore it won't be too misleading. So let us start with a vector space, we call unitary vector space. With,
First question, what's a unitary vector space?
it's just precisely what Leonid used, that vectors components are in C, in complex, with complex valued components, as opposed to real components. dimension n, so finite dimensional, and we will work only with finite dimensional space, although eventually we will be interested in studying limit n to infinity, but it's not the same as to study from the outset infinite dimensional vector space. So this comes with Hermitian scalar product or inner product, as Leonid called it, which associates complex number with pair of vectors in this space. And again, as Leonid discussed, we can write down explicitly expression for this for scalar square product of vector with itself in given basis, if we have given orthonormal basis, precisely as Leonid discussed, and we expand the given vector in this basis component-wise. We have components phi a goes from 1 to n to dimension of space, and then we have explicit expression for the scalar for the scalar product. And as again was already discussed, by the way, don't we have laser pointer or just we have a just usual point? Okay, great. So any linear operator acting in this space, mapping this space to itself, can be represented then by matrix of size n by n, dimension of space, and Hermitian or self-adjoint operators defined precisely in this way using definition of scalar of this inner scalar product, and they are represented by self-adjoint or Hermitian matrices. Fortunately, I use star for Hermitian conjugation, so it's in line with Leonid's talk, which in practice means that entries of the matrix which are symmetric with respect to principal diagonal, they are just complex conjugate. Now we start with proving in detail simple and basic formula which will be in the heart of the whole development, which we are going to use very frequently. And this comes in basically via the following lemma: define the Lebesgue measure on this vector space in such a way that this integral is equal to 1. I will give on the next view graph just explicit expression of this measure, which for brevity I denote as capital D phi. I will give it explicitly in the next slide. But let us suppose that we defined it in such a way we know that such an integral is equal to 1. Then the following is true, that the inverse of determinant of a matrix Z, in fact, implicitly I have in mind here Z should multiply a unity matrix, which has ones on the principal diagonal and 0 otherwise. But I will frequently, but probably not always, omit this trivial unity factor just for brevity and saving space. So inverse determinant of Z minus H is equal to the following integral, and important parameter in this integral is S, which is sign of imaginary part of complex parameter Z, which we always assume in such expression to be non-zero. So if this is non-zero, therefore its sign is either plus or minus 1, and this is denoted as S. So how to prove this formula? Although Leonid, I think, did not discuss this, for him it was not necessary, I hope that from general linear algebra course, you should be aware of the following fact, that any Hermitian matrix H can be diagonalized, brought to a diagonal form, by a so-called unitary rotation or unitary conjugation, by conjugation by unitary matrices. Namely, matrix Hermitian matrix H can be represented in the following, essentially uniquely in the following way: matrix, unitary matrix times diagonal matrix times Hermitian conjugate of unitary matrix, which is the same as inverse of this unitary matrix, because unitary matrices are defined as by the following relation, that the product of Hermitian conjugate of any unitary matrix with itself produces just 1, and 1 is understood as, again, as identity matrix. Therefore,
this wasn't in Leonid's, he called it spectral theorem.
Practically it is, but it's just, yes, it's equivalent to his, but yes.
The unitarity of
And also diagonalization, but in essence, it's in his, indeed, I agree, it's his spectral theorem. Now, this H is diagonal matrix of real entries, and these H's are precisely eigenvalues which featured in Leonid's talk in this spectral decomposition, or spectral theorem, how he called it. So they're all real, and this is known to hold for Hermitian operators. Now let us investigate this scalar product which features in the exponent in our integral, which we'd like to evaluate. Just use representation, precisely this representation for H. Also use the fact, replace unity, which is implicit when multiplying Z, with just left-hand side of this identity. And then you will see that this object, Z minus H acting on phi, is in fact can be represented in such a way. And now we use the standard property of this of definition, if you'd like, of a joint operator. And you see that then you can just take this U and put it to the first factor in scalar product. Now we need, for explicit evaluation of I hope you won't mind I put it here. Yes, probably it's a good idea, yes indeed, to leave it here and to use the second okay. Now here just provide explicit expression for what is understood by this Lebesgue measure d phi. It's just a product over all components of a vector. So phi is n-dimensional complex valued vector. So by d phi we understand the product of over all components of the real part of this component times differential of imaginary part of this component, and divided by pi. And this division by pi ensures this, as you may check, and this is a useful exercise, ensures precisely this unity appearing in the right-hand side of that relation. Now, look at this object here. It's very natural to introduce U times phi as a new vector. U acting on phi gives us back a vector from our vector space. So introduce a notion phi with this tilde over it. And since modulus of determinant of unitary matrix is equal to 1, as is obvious from the property of determinant of product equal to product of determinants and from definition of the unitary matrix, we immediately see that module of unitary matrix must be equal to 1. And knowing how the Lebesgue measure changes when we just change variables, it acquires the Jacobian of the and this Jacobian is precisely modulus of determinant of U, so 1. Therefore, our Lebesgue measure in U coordinates is just the same as before. So let us use this fact. We immediately see that the integral which features in the right-hand side of that imported identity can be written just in terms of new variables phi tilde immediately. just replacing everywhere u phi times u times phi with phi tilde and using this identity. And then we see if we use explicit expression for scalar product in coordinates and also use the fact that H is diagonal matrix with so it has only non-zero entries on the main diagonal, you immediately see that this integral factorizes into product of two-dimensional integral over just individually individual components from 1 to n, and moreover it further factorizes into integral over only real and only imaginary part. And then we use just the standard Gaussian integral, just standard Gaussian integral over real variable from minus to plus infinity, which in this normalization just gives us 1 over square root of a, assuming it's well-defined conversion if real part of this parameter a in front of x squared is positive. And this is indeed the case. It's precisely the case. One can check that due to the chosen definition of S, that S is nothing else as sine of imaginary part of Z, real part of this bracket is precisely positive, and also the same is here, and integrals are well defined, produce 1 over these square roots, which combines finally in such an expression, and product of Z minus HA is nothing else as inverse determinant of Z minus H, as determinant is for a Hermitian operator is just product of its diagonal entries, or product of eigenvalues. So this completes a verification of this simple but important formula, and we will use it extensively all over our lecture course. Now let us define the probability density, which is in fact Gaussian probability density, on the space of Hermitian matrices H. I will denote this probability density as d mu n of H, and this is of the following form. Essential important factors are the following. There is some normalization constant. I just defined in a way that if we integrate over all independent variables which feature here, we will get 1, so it's normalized measure. Then it's exponential minus dimensionality of space divided by 2 trace of h squared times dh, where by dh I understand the following product of differentials. It's product of differentials of all entries which are of h which are on the main diagonal, and remember they are real numbers for Hermitian matrix. Off diagonal entries, however, they are complex numbers, and therefore they have real and imaginary part. So we just consider product over all a smaller than b, because here I take product of a smaller than b because of for Hermitian matrices we already mentioned entries symmetric with respect to main diagonal, they are just related by complex conjugate. So these are independent, as it's conventional to say, independent degrees of freedom or independent variables. So d real part of the corresponding entry, d differential of imaginary part of the corresponding entry, and real part, imaginary part, and diagonal entries, they just consider to change from minus infinity to infinity. Effectively, this means that just if you look at joint probability density of all entries of this matrix, you immediately can infer, after small work, that all entries are independent. This is true. And they are identically distributed for all entries on the main diagonal, and they are identically distributed for all off-diagonal entries, although variance slightly differs for diagonal entries and for off-diagonal entries, but this is just a convention. It's just convenient to have it in this way because of convenience of this original definition. Okay. So this we define, and this measure defines a quite famous object. Basically, what I described to you is the definition of what is known as Gaussian unitary ensemble of Hermitian random matrices. This is just definition of Gaussian unitary ensemble. The name Gaussian is clear because the probability measure is Gaussian. Unitary relate, although it's important, I think it's source of many misunderstandings for people not initiated to the field, that unitary here refers to some invariance with respect to unitary conjugations, not to the fact that corresponding matrices are unitary. I'd like to stress it from the very beginning. The matrices are Hermitian, matrices H are Hermitian. But nevertheless, this measure possesses some invariance with respect to unitary conjugations, and this is the source of the name Gaussian unitary ensemble. Now, it's very easy to verify using standard Gaussian integration, which featured in our proof of lemma, of the first lemma, that the following identity holds. If I denote, and this will be the notation used in our course, by angular brackets, just calculating expectation values with respect to this probability density.
You can write that on the board.
Okay. I think it's written here. If we just define this for any object depending on h, we define these angular brackets being just a straightforward integral of this f as a function of h or with this probability density or with this measure. Then please check it. I leave many small things, and sometimes not that small, but usually straightforward things to check as an exercise. This is the first exercise. Just sit down and perform this integral. You will see that it decomposes again in component-wise integrals over all diagonal and off-diagonal entries, and then the calculation will amount to performing straightforward Gaussian integrals. And this ends up in the following useful identity, that expectation value of exponent I is just here for future use and convenience. Of course, I here is not that important. I times trace of h times any matrix k, whatever is this matrix k, is equal to exponential minus 1 divided by 2 times dimension of space trace of k squared. So I leave for you to verify this.
Is that the trace of k squared or the trace of k squared?
It's trace of k squared. It's not trace of k squared. So k. Okay. Valid question. It's trace of k squared.
Now, when you say that it can be any matrix,
yes, it can be.
exactly what you mean?
I mean that it's not obliged to be Hermitian. It's just any n by n matrix with complex entries, and still this will be valid. Of course, in particular, it's valid for k being Hermitian, but we will need it in
But the entries are complex.
yes.
And but later you will want to use this in a more general setting where the entries of k have also elements which are even in
Yes, indeed.
+1.
It will be yes, but it will be on much later stage. I don't think it's useful to no yes.
And maybe warn the audience that later this formula will be used in a setting where the matrix elements of this matrix K are taken from a commutative algebra.
Yes,
Any commutative algebra.
that's correct. Indeed. Okay. basically, our main goal in this section today, and probably also in the next lecture, is to learn how to calculate, how to perform explicit ensemble averaging, and then analysis, in fact. Analysis in the limit of growing dimension, eventually going to infinity dimension of these matrices, or indeed of the space, of the following objects. Let me explain notations. Basically, we'd like to consider product of many of these inverse determinants which we discussed in that first lemma, and as many of them as you essentially wish. Each comes with its own spectral parameter z alpha. In some particular case, all these could be equal, but I'd like to keep them different. We will need this later on. So the left-hand side, obviously, is a function of small case n. The number of terms in this product is just, I denote as small case n. So the left-hand side is some function of z1, z2, up to zn. And we'd like to find this function. Now, indices of this function, obviously it depends on size of the matrix, capital N. It depends on number of, as parameters, on number of determinants of the product, small case n. And also, for reasons which are completely unclear now, but will be more clear later on, I will put here capital index B, which stands for so-called bosonic, and I will explain the origin of this name later on. But for the time being, just I think everything here is well defined already, and we can consider this object. All important thing that I will consider all imaginary parts of all these z's to be non-zero. In order to be able to use basically this representation of inverse determinant in terms of Gaussian integral that we discussed already. So let us start with the simplest possible case.
Maybe
yes.
one word on motivation. So a newcomer to this field may wonder, why should I be interested in inverse or reciprocal determinant?
Okay, I'll tell. Okay.
If it's not interesting, people will just stop listening.
Yes, indeed. No. I think it's a valid question, although it's not at this level of knowledge. I do not assume that it's easy to explain. But okay. At the level of random suppose you have an operator, a finite dimensional operator, as Leonid described, and we'd like, and we have this probability measure, Gaussian probability measure, or any other. Indeed, one can impose many other measures. And we'd like to know various properties of the spectrum. For example, we'd like to know, in probabilistic setting, it's very valid question, how many eigenvalues fall in a given interval of real x. They are all real, so we'd like to count them, just say to consider counting measure. Or indeed derivative counting measure, which is just the density of these real eigenvalues. And in order to be able to calculate these expectation values of these products, and indeed of higher order correlation functions, for example, we'd like to know how these eigenvalues, for example, whether they are independent random numbers or they are correlated, and study these correlations. So a lot of information can be extracted from objects built from determinants and inverse determinants. In order to be able to analyze these objects, we need to introduce certain techniques. So I start with objects which are not of direct relevance for maybe even for calculating spectrum, although they can be used for other interesting problems. I'm aware of few problems where precisely these objects enter. But for our goals, this is just preparing a stage for further, or just setting the vocabulary which we will use, to evaluate objects directly related to spectrum, and indeed later on to some localization properties of Schrödinger or Schrödinger-like, I would say, operators. I hope it's enough for enough incentive to follow this presentation. If not, just wait a few lectures, although and you will see how it's used. Okay, so let us start the simplest possible case when we have just one inverse determinant here, not product of them, just single. Then we represent it by Gaussian. Precisely, we just replace this determinant, single determinant, with integral, which we demonstrated it's equal to, and then we see that the only object depending on h, which should be whose expectation value we'd like to find, is this factor in the integrand, exponential minus imaginary unity times this sine of z, which we denoted as s, sine of imaginary part of z, times scalar the following scalar product phi with h acting on phi, and then integrate. It should be averaged over this measure according to our definition. It should be. We should perform this integration, and then it should be integrated further over the vector, and then we get the left-hand side. This is obviously the procedure we should follow. Okay, so the main goal is to show how first to perform this average, and then how to analyze the corresponding integral, especially in the limit of large size of the matrix, which is our main goal. Although we will get a closed form result already for finite n, but we will be most interested in large n limit by various reasons. Okay, it's just convenient to associate with each vector of our unitary vector space of dimension n a pair of rectangular conjugate matrices, or better to say, a pair of conjugate matrices of rectangular form, which in this case, or just when we have only one vector phi, so with every vector phi, we associate two rectangular matrices. One is just vector itself considered as a matrix with one column and n components, just entries of this rectangular matrix. And the conjugate matrix is just the row of n numbers made of complex conjugates of the corresponding components of vector phi. So with every vector phi, we uniquely associate two matrices. Now, looking at them as the matrices, we can form two products. We can multiply phi. Okay, in order to distinguish these matrices from a vector itself, I just added these heads. It's just for notation which allows us to see whether we deal with, we look at these objects as matrices, or indeed of this form, or we deal with a vector from the corresponding space. It's useful to keep this distinction, although they are directly related. So these heads precisely stand for this distinction. Now we can form product of phi and phi and conjugate of phi in two different ways. We can multiply. You see that according to rules of matrix multiplication, we can multiply them in any order. We can multiply phi with phi, phi conjugate, or phi conjugate with phi, and the result will be obviously different. First of all, it's just trivial fact to observe that if you multiply phi conjugate with phi, then just it's immediate to see that what you get, you multiply row with a column, so you will get one number, and it's immediate to see that this number is nothing else as scalar is equal to scalar square of the vector phi from our vector space, which we introduced before. On the other hand, if you multiply phi with phi conjugate, so now you multiply, okay?
Also, convention considers the conjugation in Y?
Conjugation is, I think it's just given here. So if phi is defined like that, you then build a row vector of complex conjugates of all components. This is the definition of conjugation. Now, let us consider product of phi with phi conjugate. This is a product of a column, matrix of a column with a row. So obviously the result will be n by n matrix. But this n by n matrix, it's very specific one. And again, I probably should write it down as an exercise, but it's very easy exercise. Just to find eigenvalues and eigenvectors of this n by n matrix, which is formed in this way. And you will find that this n by n matrix, it has unit rank, which in practice means that it has only single eigenvalue, which is not 0, and n minus 1 eigenvalues, which are precisely 0. Moreover, please use, this is simple but useful exercise, I think. Just find eigenvectors explicitly of this matrix, and you will see how they are related with phi itself. And the only non-zero eigenvalue of that matrix is precisely this scalar product, which is equal to a product of phi conjugate with phi itself. Okay. This is the first observation which we can make using those vectors. Second observation. Further note that, consider the following object, trace of h times phi times phi conjugate in this order. That's important. Then using just cyclic permutation under sign of trace, you trivially check, you just make this cyclic permutation, which is allowed under sign of matrix trace, and you find that this is nothing else as scalar product of phi with h acting on phi. This is just the same object as is basically immediately clear, and therefore this exponent of minus is times this scalar product can be written down as exponent of minus is trace in this form. What is the purpose of writing this? The purpose is simple. Now we can use this, I think it was our second lemma.
You still have it here. The third line.
Yes, yes, indeed. Yes, precisely. To use this, thank you. To use that lemma, and then we see that effective averaging is very simple, because it amounts to taking trace of squared of matrix phi times phi conjugate. But we know that this matrix is of rank 1, and therefore has only a single eigenvalue, and then it's trivial to calculate a trace, because trace can be always calculated if you go to eigenbasis, and then it's just sum of eigenvalues. So we immediately arrive to the following formula that basically all this preparation shows us that performing ensemble average over Gaussian probability measure is very simple. The result will be given here.
One thing here.
Yes.
I look at that formula.
Yes.
It says that I should the factor of I in front, which is good.
Yes.
Have that.
Yes.
And then I should look what multiplies h, and that's called k.
K. Yes.
That thing that.
It's phi.
What you're writing here.
Yes.
The middle expression has an s.
Yes, indeed. This is a number.
So here that disappears, but later.
Yes, later it will be important. Here it just trivially disappears because it's plus or minus 1 when squared. So basically, to be as precise as Martin wishes, here object K is S times this matrix, which is still rank 1 matrix with eigenvalue equal to S times that eigenvalue that we discussed. And then when we square it, S just disappears because it's plus or minus 1 squared equal to 1. Later on it will be important, but later on I think I will be more careful, hopefully. Okay, so this is, now we see what is the result of our ensemble average. It basically amounts to performing such an integral, which by some reason, which will be clear later on, by some technical reason, I prefer to write down using equivalence between scalar product and matrix product taken in this order. I will write it in this way. Just trivial rewriting of the above equation. Now, what we in fact can immediately infer from looking at this formula, especially in this form, but implicitly also in this, that if one considers rotations of phi with arbitrary unitary matrix U, then basically this expression in the integrand is invariant with respect to such a rotation, because scalar product is invariant and the measure is invariant. So we see that basically we deal with situation when integrand is invariant with respect to some group operation. Basically, in simple terms, in this particular case, we all very much familiar with such situation when we'd like to calculate integrals say in three-dimensional space, and everything depends only on integrand depends only on distance between points in this space. It's natural to go to so-called spherical coordinates. And basically, what I'd like to discuss here and later on is just a little slightly fancy analog of this simple procedure. But in this case, it's literally going to spherical coordinates. It means instead of phi, I'd like to use the following coordinates. I'd like to use the length or norm, as Leonid introduced, of phi, or rather, in fact, I use scalar product, which is squared norm, and denoted as r. It's not, in fact, I should put it, it's non-negative, and the rest is just will be the vector with scalar square equal to 1, obviously. So I just decompose variables in these two parts, just its length and rotations, which live on unit on a sphere of unit radius of this in this space. And with such a decomposition of a vector, there is a natural decomposition of matrices, this phi hat and its complex conjugate. Namely, basically it induces the following decomposition of these matrices. Namely, phi can be represented by product of unitary matrix acting on a vector, column vector, which has only single non-zero component in its first component, and the rest just n-1 components are 0, and also just some phase factor where alpha is just a real number. I write it here. It's not very clear why I should go in this way, but later on we will see that similar decompositions are also possible when we consider products of average of products of several determinants, and then they are quite handy. Okay, I can write down this measure in new variables. I write it down, it's here explicitly. It's just radial part, and angular part associated with this decomposition is just suitably normalized, say, to 1 invariant measure on set of unitary, on manifold of unitary matrices, which is group UN.
But Jan, I have a little bit of a problem now.
Yes.
Because you write equality sign. You know.
You mean that it's okay up to okay.
Sign.
I always can absorb if you ask about suitable normalization, right?
No, but this is an equality where it's an equality of Lebesgue measures.
Yes.
But
yes.
The two spaces are of different dimension. On the left-hand side, you have a complex space of dimension big N.
Okay.
It's Lebesgue measure. So it's real dimension 2n, complex dimension n. On the right-hand side, the Haar measure, the unity group, has dimension n squared. The Haar measure is a Lebesgue measure in the space of nonlinear space of n squared dimensions.
Mm-hmm.
So, you know, mathematically, you cannot write equality when
Okay.
there are measures on different spaces. And the background is that you're calling it a parameterization, but it has redundancy.
Yes, indeed. You mean that it's not full, okay. U is not arbitrary matrix. In fact, there is a, yes, redundancy in U.
Changing U without
Yes.
changing.
Without yes, indeed.
So
you should
bijection.
You should factorize it, but
Or,
yes.
I mean,
That's
I'm
correct.
not good about this notation. It's an equality under the integral sign.
Yes, indeed.
So
If you calculate,
integrate
yes.
functions with the proper domains, then you get the same answer. So in this sense, it is an equality. But
I completely agree with Mark, and yes, please correct me if I will be a sloppy at that later on. Yes, indeed, one should understand it as identity between corresponding integrals in the left-hand side and in the right-hand side. Okay. Oh, I probably leave it here. Slightly worried. Let me just see that one. Okay. Okay, now let us just then, using the fact that it's an equality on the integration sign, let us just use this this type of equality here. Then also it's just convenient, you will see in the moment why it's convenient, just to rescale radial variable r with factor n, which comes from dimension. So just trivial rescaling of integration variables. And then you will see that the resulting expression for, now it's our left-hand side depends only on one complex variable z. And we see that up to an explicit but less interesting constant, we are dealing with the following integral. It's exponential minus something, some function of r, proportional to size of this matrix n. And we also have dr divided by r. And this function L is given explicitly here. It depends on z, of course. Now, for finite n, we cannot do better. It's just the answer. We can try to perform this integral explicitly if you wish to do so, but we are not that. In fact, it can be related with some transforms of Hermite polynomials, but we are not that much interested in that. Our main goal is to understand how to extract asymptotic behavior of this integral in the limit when n tends to infinity. This parameter n tends to infinity. And integrals of this sort, it's very well known how to invest in principle. I won't go into detail, which could be relevant when you perform this, and one should take appropriate care, but the general strategy is clear. If you have integral of one, or indeed, in the end, many variables, and your integral depends in such a form, then you should apply what is known, I think, in mathematical literature is known as Laplace method, basically, in the case when this r is, integration goes over real axis, but it's in fact just also known as steepest descent method. So technically it amounts to finding the stationary point of this function L, which features in the exponent, and then deforming a contour. If it happens to be not on the real axis, then one should deform integration contour from the real axis appropriately to allow it to pass through through the corresponding saddle point in appropriate way, ensuring that it dominates the integral. So if we have several these solutions of the corresponding saddle point equation, one should take care in considering all of them and extracting contribution from all of them if one can deform contour to pass through all of them. But technically one just differentiates this over R, and then one finds that solutions are given by this. It just amounts to solving quadratic equation, as you may see. And this is the corresponding solution. I'd like to restrict our consideration to as simple case as possible. Therefore, I consider real part of Z equal to 0 and imaginary part of Z. In fact, we kept it non-zero from the very beginning, but in the end, I'd like it to allow it to tend to 0. Okay. Then we see that in this limit, in fact, solution is as simple as possible, just equal to plus or minus 1. Why I'd like this choice? Because it's immediately clear, without further consideration, that for our integral, which extends from 0 to infinity, the only relevant saddle point here should be 1, not minus 1. Because this is basically what our integration domain dictates us. So we pick up this contribution. Then we, apart from just substituting this solution to our integral, we should also calculate, expand L up to second order. First order will vanish because this is precisely saddle point. So you will have second order in deviations from your saddle point. So it will amount to calculating straightforward Gaussian integral. And here is the result. It's basically, for illustration, here, so I won't discuss it any further. Just please do this and check that all factors, I hope I did it correctly, so all factors combine to such an expression. So,
why are you interested in the limit of z going to 0?
Okay, in principle, all the same procedure can be done for any complex. In fact, we started with Z non-zero. Again, applications dictate this, because we shall see later on, at a later stage, when we will apply these integrals to investigate some spectral properties of, or better to say, some properties of spectra of these random matrices or indeed operators later on. We shall see that it will be precisely the limit we're interested in. It also, we shall see that it's not just arbitrary. Here it's not clear. In this example, we just said it tended to 0. But later on, we shall see that we should be very careful in the rate of at which it goes to 0. And the most interesting results will appear, not for this object, but for more general objects, when this imaginary part is kept inverse to the size of the matrix in such a way that its product with size of the matrix is finite in this limit. So it again, this is just dictated by further applications. But in principle, of course, here there is no particular reason. You can investigate this simple integral. It's simple enough to be investigated for arbitrary z.
So the short answer is that the spectrum of a self-adjoint operator is on a real axis. To probe the spectrum, that is where you want to push the parameter to. This is where this thing is singular. Singularities of this function omega are on the real axis, and he's going to the singularity.
Allows to these objects will then feel these eigenvalues and can
Doesn't it come from the fact that you have assumed that your probability density is centered around 0, and why a priori you assume that your exponential is centered around 0, trace of 0?
No. It's just completely general. I mean,
the real part. That would relate to the real part of
this is the fact that I centered, yes. But you see, for didactic purposes, in all cases, in all examples which I consider, I always consider the example I personally consider the simplest. So, because otherwise we will go into too many detail, but be aware of the fact that all these statements can be made in full generality. In particular, one can consider arbitrary values of z. But just for demonstration purposes, I took the simplest possible example. And I will keep doing it almost all the time. Okay. Now, here I just showed you one way of dealing with this integral, and it was good enough. But I will keep solving this random matrix problem in two related but technically different ways, and with a good reason. In fact, if you try to generalize this method, we introduce some methodology, basically some techniques. Later on, they should be applied to some hopefully diverse set of problems. And we won't be able to see it directly. Maybe I will comment in the very end. But I will give you two slightly different variations of all these techniques. And those could be useful when applied to slightly different types of problems, of actual problem in disordered systems. And also it's nice to have different methods or slightly different methods, because they could give us some insight under certain circumstances. So I provide you with an alternative way of analyzing this integral. And for this, in fact, okay. So so let us come back to this line. There is a different way of analyzing this integral, not going to this polar coordinate representation. And in physical literature, this way, in fact, is preferred, usually. And it's known by the name of the Hubbard of exploitation of what amounts to a simple Gaussian integral, but it has name in physical literature, name Hubbard-Stratonovich identity. In fact, okay, just again, small, it's not warning, but just explanation. I do not provide any references to original papers or even reviews or whatever. What I plan to do in the very end, I'm writing now basically the list of relevant references with small comments to which part of this lecture course they are relevant to, and I will distribute it in the very end. So I might from time to time mention some names, but in no way I'd like to go into discussion of the literature. So during my my lectures, but you will have access to all literature I believe to be relevant for this course in the very end. Okay, so this goes as Hubbard-Stratonovich identity, and basically it claims that the Gaussian one-dimensional, just standard Gaussian, almost standard, I will explain you, almost standard Gaussian integral in the right-hand side is equal to the left-hand side. If I put here this scalar product to 0, you will see that it amounts to just standard Gaussian integral equal to 1. This is indeed standard Gaussian integral. Here it's just slight deformation of standard Gaussian integral, which one can derive in many ways. I just leave to you to derive it in whatever way you wish.
But that's the integral that you did before, in a sense.
Without shifting, in some sense.
The first.
You mean with this identity? Yes. Yes, in some sense, yes.
The same thing as this.
Yes.
This is the one-dimensional
Gaussian integral, yeah.
Special one-dimensional case.
Yes, you can complete the square, for example, and then shift the contour or whatever, in whatever way you may understand this. But this is standard, again, standard Gaussian integral. But it's read from left to right. Usually we have integral equal to something simple. Here, just the trick, on first glance trivial, but really very helpful, and also appears not only in this domain of application, but it's in fact extends also to theory of phase transition. I think in some of lectures it will appear maybe in different disguise. But basically, it said that if we have bottom line is that exponential of something squared can be always rewritten as integral of exponential linear in this object, if it's convenient for our goals, paying the price of extra integrations. So this is the essence of this formula. So then we are back, let us apply it to our integral. We have this integral, and we exponential of this object we just replace with such an integral, and we also assume, or in this case one can easily verify it, that one can interchange the order of integrations, and then we see that integrations over phi are easy to perform because it's just basically, if you write down scalar product in components of vector phi, you will see that it decomposes in a product of one-dimensional, or basically two-dimensional, because phi is complex, two-dimensional component phi's integrals. And these are standard Gaussian integrals, again, convergent because of S being chosen precisely the sign of imaginary part of Z. So then you perform this integral. And you are done. You have then, you're left with one-dimensional integral with Gaussian factor, but also with a factor of this form. And so you have 1 divided by something to n. Write it down as exponential minus n log of this something. Rescale q tilde appropriately, and you will see, rescale it with square root of n, rescale the square root of n, and you will see that your integral is again of the form which allows this saddle point method to be applied for analysis of its large n behavior. I do not do this analysis here. I leave it to you as an exercise to verify that the result will be precisely as that which we arrived by the first method. It's, by the way, again, useful exercise. Please do it.
Well, maybe we can pause here for a second. It should certainly be the same for n going to infinity, but already at any finite n.
They're also, of course, just, yes, of course they're equal because it's just identity transformation.
Right, and stare at it for a second. So
okay.
You have two formulas for omega 1, nb. One formula coming from the spherical coordinate. Integral.
Okay. Maybe I won't be careful enough. Just this one was square root of 2 pi. I think it's not that important for. Okay. Okay.
No, we don't need.
We can write it here. Integral. Exponential. I already rescale. I think it will be useful. Minus n
log.
minus n log of z plus sq tilde. That's it.
You rescale.
Yes, I already rescaled.
And, you need
and here?
the first q also needs a tilde then.
Yes, indeed. And q tilde and d q tilde. And it will be of course factor square root of n here, coming in front because of rescaling. So this is equal to, okay, we should have it, the formula here. This is equal to some constant depending on s, integral from 0 to infinity, exponential minus n, okay, r squared over 2 minus is zr minus log r, bracket is closed, dr divided by r. So I'm not sure that you wanted it in this form, but
Is it possible to verify this directly?
of course, yeah.
Put this as an exercise to the student?
Please verify it directly. Indeed, it's possible. One can do it. It's not that simple to see. To verify it directly. But in fact, via some transformations, one can do it. But it's not simple.
I know that in more complicated cases, which you're getting to, I'm not able to show this directly.
No, in this case,
I
one
need to know that these are the expressions for a certain function, which is the same in both cases.
If you'd like.
One uses method number 1 or
Okay,
method
I know
number 2.
other. Okay, a possible way is first to understand that this is nothing else as some disguised Hermite polynomial, and then use two different integral representations for Hermite polynomial in complex plane and just usual Gaussian representation.
It's rather complicated.
So,
We
yes.
will not know how to show this.
No, that's why I decided not to give it as an exercise. But in principle, there is a way, but it's complicated. It's not that simple.
So there are two integral representations for the same object as expectation of a inverse determinant, and they're both correct, so they must be equal. But it's not clear to prove this as it stands, without going to some deeper knowledge about Hermite polynomials.
Yes. Without this, I don't know. This is the way I know how to verify it. Okay. So let us now extend this method for n larger than 1. So we consider basically extension will be rather straightforward, although maybe notation sometimes more, definitely there will be more involved. But the idea is very, first steps will be just a repetition of this simple n equal 1 case. So again, now we consider product of many, expectation value of a product of many inverse characteristic polynomials. And individually, we replace each of these inverse polynomials in the product with their representation via our first lemma, via Gaussian integral over vectors phi. So we will have altogether as many of these integrals as we had inverse determinants. So small case n of them. And just combining this product of integral into one integrand, we will see that what we need to perform average of is exponential minus I sum over all alphas going from 1 to n. So alpha goes from 1 to n, is obvious. These factors S alpha, which we do not assume they are all the same. In particular case, all imaginary parts may be of the same sign, but we will see that this is only one and the most trivial case. And interesting cases appear when at least some of them are of different sign from others. But here we just have them as they are. And we have these scalar products. And similarly to the case n equal 1, we introduce two conjugate matrices associated with, so we have now n, small case n, of capital case n component vectors, and let us arrange them in two rectangular matrices. Namely, one is of this form where phi's vectors, they are just used as the columns of this rectangular matrix, and obviously its conjugate will be just by usual rules of Hermitian conjugations. Corresponding phi's will be replaced with components will be conjugated, and they will be arranged in the corresponding rows. So I here show the structure of the corresponding matrices, matrices phi and its conjugate. Now, first form the product of this with that. We obviously, okay, just make this in the usual sense of matrices, you can consider this product, and you immediately see that this generalizes the case of n equal 1. In case n equal 1, taking product of phi conjugate with phi gave us just one scalar product. In the general case, this will be the whole matrix of size n by n, where n is the number, number of determinants in our original product, and it will, all entries of this matrix will be made of mutual scalar products of between all possible scalar products of phi inside this set of phis. So this is just scalar square. The next term will be phi 1 with phi 2 up to phi 1 with phi n, and basically it's Hermitian matrix, so it's enough to specify only structure above the main diagonal. So it's Hermitian matrix, and it's positive definite if all phi alpha are linearly independent. Otherwise, it can be, but it's proper to say that it's non-negative. So its eigenvalues could be 0 if some phi's are linear combinations of others. But generically, if it's not so, this is positive definite Hermitian matrix. And this will be important object. We call it capital R. In fact, you see why I call it capital R as a matrix, because it generalizes just scalar product phi with itself, which was used as a radial coordinate in that decomposition. So it will be precisely the same role will be played by matrix R here. Oh, I leave it here and okay. Now we have Hermitian positive semi-definite, I think correct name for it, matrix R. So it can be diagonalized by un rotations. So take matrix V from unitary group. So any R can be written down in familiar way. We already used that Hermitian matrices can be diagonalized with unitary matrices. Here, just it's useful to remember that all eigenvalues, which I denote R1 to Rn, they are non-negative. Now, we can ask ourselves the following question. Let us introduce the following Lebesgue measure in space of all Hermitian positive definite matrices. Let us introduce them in the same in our familiar way as a flat measure. This is called in literature flat measure, just product of all differential of all independent degrees of freedom or entries. It means product of all differentials of real values on the diagonal and real part and imaginary part of off-diagonal entries. But then this measure is written in terms of entries of matrix R. But suppose we perform such a decomposition, just diagonalization of the matrix. How this measure will look in terms of eigenvalues and these diagonalization matrices V, which are built of eigenvectors, in fact, as is easy to see. This is a standard problem. It's not a completely trivial problem, but it's basically a standard problem in random matrix theory. I give here just the answer for it, because deriving it would require considerable time, which I do not have. But here is just the result. So if you perform such a transformation to variables, this amounts to calculating the Jacobian of coming from entries to eigenvalues and eigenvectors. Then the corresponding Lebesgue measure up to a constant, depending of course on these variables, given by the factor which is known as squared Vandermonde determinant, but amounts to squared product of differences between all eigenvalues going over all distinct pairs of indices alpha and beta. Here's just product of all differentials of R's, and then suitably normalized Haar measure on the unitary group.
Same comment as
The same comment, I already prepared to say it. The same comment, this identity of measures is understood in a sense under integration.
maybe we can discuss why. If you ask how many degrees of freedom are in R, then the answer is n squared real degrees of freedom. This
Yes.
is what a Hermitian n by n matrix gives you. On the right-hand side, it's n times n plus 1,
Yes.
because you have n squared degrees of freedom going into the unitary group, and then another n for the eigenvalues.
If you just multiply u with the diagonal matrix of this v with just diagonal matrix of these phases from the left, then it's easy to see that it just these factors are just cancelled. Therefore, this is a redundancy, in fact, essential redundancy that Martin is speaking about. It's useful to have in mind, yes, indeed. But I think, okay, this comment is clear.
Another question, does everybody understand what is meant by Haar measure? Can we assume that? Or should we explain?
Just measure which is left, and then one can show right invariant, and which is with respect to corresponding group multiplication, and it exists for any, it's unique for any compact group, but it exists also for non-compact groups in many cases. But if you can give more on this.
It's infinite time on it. I just want to get some feeling for what the, but some people nodded, so I take it that we can assume everybody understands Haar measure.
Okay, maybe one can give it just, if you consider on a sphere just spherical coordinates, in fact it provides such on a unit sphere such a measure for O, or say n, if you consider it. Or on a circle it will be just d alpha, in fact, for u1. But in other cases one should construct it explicitly. Okay, now it's convenient to introduce, we remember the presence, and this will play, this presence of these factors plays later on important role, these sign factors which take care of sign of imaginary parts of all these. Let us arrange them, we have n, small case n of them, let us arrange them in a matrix S which has them as diagonal entries. Then just, I have to accelerate slightly, then just straightforward manipulation using trace permutation to check that this sum can be again represented in a way which will allow application of that nice formula of averaging exponential of trace of h times another matrix. This is precisely the form I'd like to arrive at. Here, this S is taken care of. That's what Martin wanted last time. And then we just see that therefore it amounts to the result of ensemble average is again simple. It's minus 1/2 trace of this object squared. Again, it's not trace of this object and then squared, but trace of, so this object should be squared and then trace should be taken.
I have another question.
Yes.
So now here you speak about the measure dr, but on the previous slide you had the measure product over d phi alpha.
Oh,
The same?
alpha? Here there is no alpha.
So in this slide, in this integral, you have the measure d phi alpha.
On the previous one, it was d alpha. The analog of that, because we had there only one this factor alpha.
But here you have product over d phi
Where's
alpha.
it? You mean this?
So is this
this.
the same? Is this the same as
It's just okay. Originally, just product of all independent real and imaginary part of the of entries of this vector phi.
How is it related to dr?
We will discuss it later on. It's it will be a topic of our next slide. I hope to be able to give to you.
For the phi's, there was a natural normalization convention, which is that a certain Gauss integral should be equal to 1. That determined the normalization here. For dr, maybe there's something similar.
We will discuss it. We will at least I hope that it will be an answer to your question. I will put it already here in order to satisfy, but I will come to this just a few moments after. We're approaching it. But the bottom line is that ensemble average produces the factor exponential minus 1 over 2n trace of our matrix R introduced. You see this matrix phi, phi conjugate phi. It's our matrix R times matrix diagonal matrix S again times R times S. This is the bottom line. Therefore, we arrive to the following representation of this product of inverse determinants. Just okay, it's written here. And now we need to know what is this d phi. So this is precisely your question as far as I understand. In new coordinates. Okay. In full, okay, but these coordinates were not yet introduced in full. Now, in full analogy with case n equal 1, we introduce the polar parametrization, which is now also frequently in the literature is called singular value decomposition. Just you can find it in, I think this is even more frequent name for it. For a pair of matrices, of rectangular matrices phi and their Hermitian conjugate, namely these phi's, again up to certain redundancy, which I don't like to discuss, but which is always present, as Martin mentioned, it can be represented as a product of unitary matrix, then the matrix which has n columns, but has non-zero entries. Basically only so this size is capital N, this size is small case n, and I tacitly assume that small case n is always smaller than capital N, which makes sense in notation. In fact, larger or equal. We shall see. Then one can show that this is parameterization which we can use in terms of two unitary matrices. Matrix U is unitary matrix from group U capital N. Matrix V is from U small case n. In the simple example n equal 1, this I call them this exponential of I alpha. This is basically was parameterization for U1. And now one need to calculate the measure in these new coordinates. This is again not that trivial exercise, but can be done. It just amounts to calculating the Jacobian. And just Jacobian factor can be calculated by some work done, or you can find it in many books. Not that many, by the way. This calculation, not that many, but I know at least one book where one can find this calculation explicitly. Or you can do it yourself. In fact, I recommend you, it's very instructive, to do all these calculations for small case n equal 2. It's already non-trivial because n equal 2 requires a matrix, not just scalar, as it was in the first example. But it can be done by hand just within half an hour, and or even maybe less for time, or longer for other. But it's really exercise which one can do by bare hands, and it's useful, and you can verify all, basically n equal 2 or larger case n, they are not that much different. So I really recommend, it's very instructive. Anyway, you can do it. You arrive to this formula, and then you just, by comparing this Jacobian factor with Jacobian factor which comes in this measure, you see in parameters in eigenvector eigenvalue parameterization of R itself, but just by comparing them in 2 slides, you immediately see that in fact Lebesgue measure in new coordinates can be represented as measure dr times determinant of R to power capital case n minus small case n, assuming that this is larger or equal to a, times Haar measure on U. And this, as basically nothing in the integrand depends on this U, as it's easy to see. It's very easy to see that all this U is basically redundant variable. Its integrand is invariant with respect to this notation, this rotation, the unitary rotation. It can be integral over U can be performed. It gives some constant because U is the mu is Haar measure, so appropriately normalized, so it gives some constant. And we are left therefore with the following integral representation for our object, which is straightforward on one hand, maybe less straightforward on the other hand, generalization of this representation, which featured in the right hand side in the simplest case n equal 1. So I have 1 minute, so just let me summarize. Our goal next time will be to show how to analyze this large capital N behavior of this integral for first when S is just identity matrix. So it means that all, but this will be very simple. Just when all imaginary parts lie in the same half of complex plane. But then we will see that when S is not proportional to identity matrix, so not all of them positive and negative, but parts are negative and the remaining part is positive, it will require much more effort. The analysis will require much more effort and will be demonstrated on Wednesday, I think. Thank you.
We will usually aim to have enough time to just ask questions at the end.
I think in the meantime, I think it's
Lecture
better.
should try to shoot for 75 plus 15.
It's very hard. Very hard.
In that spirit, if there's something urgent or something useful or that might help, please feel free to ask.
And of course, if later on you realize that you'd like to ask something, just approach me directly, and I will try to. And if this question is of general interest, I will then probably invoke it next time in front of all of you.
You can also comment on the style, the speed, and all these things. You can also just approach any one of us, preferably me, in private, with comments on the lectures.
Yes, please.
If there's no response from the audience, then we have a lunch break. I believe that is an hour and a half, and we reconvene at 2 o'clock for the second lecture by Leonid Pasteur.
I was one slide shorter than I